Right. Good morning, everyone. Today, we're going to be looking at a few of equations and concepts that we'll cover in Unit 6. So we've already talked about static fluids, pressure at depth, Archimedes' principle, and the buoyant force, as well as in our lab, we talked about Young's modulus. But today, we're going to focus on what happens when fluids are in motion. And so there are two main equations that will describe what we'll look at when we are considering things in motion. And the first is going to be what is going to be referred to as the continuity equation. And on your formula sheet, it's going to list it as continuity. All right. And the general idea here is when we have a pipe and there's a fluid moving through that pipe, that fluid is going to have a velocity and it moves. And the general concept is that the volume flow rate through our pipes, through this motion of the fluid, is going to remain consistent. That's kind of where this whole continuity equation is going to build from, that the volume flow rate through a system, through this pipe system, is not going to change. And if it's a straight pipe, that makes sense. The velocity at one point is going to be the same throughout, and the flow of fluid is constant. It can't go faster in one area than another because there's fluid. It's fully submerged in fluid, and the fluid has to flow at a certain rate. And so volume flow rate, the idea here is a change in volume divided by time, right? So that's our idea. But the real question here is what happens when it's not just a constant, when it's not just a constant or same pipe, but what happens when the diameter of that pipe changes? Whether it either restricts down to a smaller diameter or the opposite could occur as well. Our diameter gets bigger. Well, the continuity equation says the volume flow rate must remain constant. So what does that tell us? That means the change in volume per time in our wider area, in this area right here, is going to be the same in the volume per time in this smaller area. So we're going to build out this equation a little bit. The idea here is we can imagine if we were to take a section of this pipe, maybe this section right here, the amount of volume of fluid that's passing through this, and you'll notice this is the shape of a cylinder, is the same as the amount of volume that passes through maybe a section over here through a similar period of time. But we're going to expand out this change in volume, and the area of our cylinder, right, our volume of our cylinder equation is really that cross-sectional area, which for a cylinder would be pi r squared, times this, we'll call it d distance, right? We'll call this d distance. And we're building to our equation. Because now we can see that we have a equation, a relationship here that we've seen before, distance over time, right? And so distance over time is the same thing as velocity. So our real equation is actually going to be this. What we're going to say is the area times the velocity, meaning how fast the fluid is moving, is going to remain constant. And so the way that would look is A1V1, so the area and the velocity through one section is going to be equal to the product of the area and the velocity in a second section. So this is the continuity equation right here. This is our equation of continuity. And conceptually, it should hopefully make sense. The idea here is as the area gets smaller, in order to the volume flow rate to remain constant, the speed of that fluid has to increase, right? If you've ever put your thumb over the end of a hose when you're playing with it, you know that the water is going to come out faster when you restrict the size of the opening. That is the concept we're looking at with this equation. The smaller the opening, in order for the volume flow rate to remain the same amount of fluid to pass through that area over the same time. Since the cross-sectional area is smaller, the fluid must move faster, right? So again, imagine putting your thumb over the end of a nozzle, or you have an adjustable nozzle, the jet spray, the jet setting is the one that has the smallest opening. It's where the fluid is going to fly out the fastest. So this is our continuity equation. A1V1 equals A2V2. All right, so that is our first kind of big idea when we talk about fluids in motion. But the continuity equation will also lead us into our next formula. But before we do that, there is a concept that we want to think about. And that concept is, how does this relate to pressure? We have an increase in speed. When we have an increase in speed, we're going to have an increase in kinetic energy. We're going to have work that's been done, right? And so there must be a force. There must be something that's propelling it and pushing it forward. And in our context, we're going to think about that in terms of force per area, or in other words, as pressure. So where is the pressure going to be greatest? We have a pressure in a slower moving area where we have a wider diameter, and another pressure in a smaller diameter where the volume is moving faster. So is the pressure moving, is the pressure going to be higher in the slower moving, wider pipe, or is the pressure going to be higher in the faster moving, smaller diameter pipe? And the answer is the pressure is actually going to be greater over here in the larger pipe. So our pressure actually ends up being greater in this section right here. And so I want you to think about this in a few ways. I want you to imagine maybe you are squeezing out some toothpaste onto your toothbrush, right? And so where do you push? The wider area is where you're squeezing, and where you squeeze this wider pipe. So you're going to imagine that you're squeezing this wider pipe right here. We're putting pressure, we're squeezing it in here. And what does that do? That causes the fluid to get pushed and move faster through this smaller area. So we have a high to low pressure. So our high pressure is where our fluid is going to be moving slower, and where our fluid is moving faster is where we're going to have a lower pressure. So imagine squeezing a toothpaste tube. You squeeze in the wider opening to shoot toothpaste out the smaller area. This also has some interesting implications in if you're designing the wings of an airplane. All right, what's the purpose of a wing? How do we generate lift? So if this is the wings of an airplane, the general goal of the airplane wing is to do what? It's to move air. And which way does it want to move air? Does it want to move air underneath the wing or on top of the wing? And it would actually want to move air over the top of it. What does that do? Well, when the air is moving over the top of the wing rather than the lower bottom section of the wing, that air up here is moving faster. We now know that faster moving fluids have a lower pressure. So if we have all of our air moving faster on the top, we get a low pressure on the top, and we get a high pressure on the bottom. And now we have a pressure differential. And so, therefore, we are going to have an upward force. We're going to have a lift, right? And so this is how you're going to design, an airplane wing to move the air in a certain way to lift the airplane up, right? If you've seen a car move really, really fast, or a boat moving really fast, you might see it almost lift up into the air as it going. That's because the air is moving over the top really fast. Or we live in Texas, so we know certainly there are tornadoes that can come. And when a tornado comes and it flies over your house, you got to be cautious. If the wind is moving too fast, what happens? The tornado is moving, and that high speed air is moving where? Over the top of your roof. Inside your attic or inside your house, the pressure is going to be high because the air is not moving nearly as fast inside your house as it is outside. Fast moving fluids, low pressure. And so what happens in a tornado, the air moves really, really fast over the roof of your house, generating a low pressure, and it sucks your roof up almost like a vacuum due to that pressure differential. So that's why you'll see oftentimes things flying up in the air during a tornado or a hurricane, right? Roofs getting pulled up and off. It's not that necessarily the wind is traveling underneath the roof and pushing it up. That might be a little bit of it, but the bulk of that force is actually from that pressure differential. And so the faster moving fluid is going to have a lower pressure. All right, so that is our concept behind this continuity equation. All right, so now we are going to have one other concept that we're going to look at. And this last concept is going to be called Bernoulli's equation. And on your formula sheet, it's going to list it as Bernoulli's law. And before we give the full equation, let's talk about the concept real quick, and we'll kind of pull the equation out of a familiar one. And the familiar equation we're going to look at is Bernoulli's law is really just going to be expanding our conservation of energy equation for fluids. So what's our conservation of energy equation? Well, that would be the kinetic energy, so 1/2 times mass times velocity squared, right? Plus any potential energy we have, mass times gravity times height. And the idea is, as an isolated system, that is going to remain constant. So we might say at point 1 is going to be equal 1/2 mv squared at a new location, point 2, right, V2, plus our potential energy at our new location, height 2, right? Now we're going to put a little bit extra here because we know not all systems are isolated. We might do work on our system as well, right? So if we do positive work, we know we end up with more energy than we started with. If we do negative work, we know we're removing energy, and so we end up with less energy than we started with. But this is kind of our general equation here, right? That work plus kinetic energy plus gravitational energy equals 1/2 mv squared plus mgh as well. And so the way this is going to look in a fluid problem is you might see something along the lines of this, a problem that looks, see if I can draw this with my mouse, something along the lines of this. And the idea is we have a few things here. We might have a wider pipe getting restricted to a smaller pipe. We know that's going to change the kinetic energy because it goes from wide to small. We know that's going to make the velocity of that fluid go faster. And you might also, you may not, but you might also have a change in height, right? The pipe might go up or it might go down. There's certainly going to be problems where the height doesn't change as well, but this example would include kind of all of those scenarios there, right? And so we can see how the velocity might change. And maybe in a problem like this, you would be given something like the diameters, right? One velocity and both diameters. And maybe we have to use continuity equation first as a first step to find what both of the velocities are. And then we can plug it in to our velocity 1 and velocity 2 here in this Bernoulli's law equation. And the height we would certainly need to be given, right? We would say, oh, well, it either stayed at the same height or it went from one height, what we would call 0, to some new height, and we would plug that into the equation. But the issue with this problem as it is what do I use for mass and what do I use for work? What do we plug in there? This is a fluid that's moving through. So what are we going to use for mass? Well, it makes it a little confusing. And so we're going to change up our equation to make it easier to use, right? So let's derive our actual Bernoulli's law. And so what's our equation for work? Instead of work, we know we have a different formula for work. We're going to use force times distance, right? I'm not going to worry about any sine or cosine for this one. So force times distance here, that's another version of work. And we have mass, 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 mass. So what's another, when we're talking about fluids, let's think, what is another quantity that's really easy for us to use if we're talking about water moving through a pipe? So that equation, that formula, instead of mass, let's remember density, because the density of water is a known value, right? And so density of water is 1,000 kilograms per meters cubed. So instead of mass, what if we could substitute in density here? Because I know density is mass per volume. So here's what we're going to do. We're going to take both sides of our equation and we're going to divide it by volume. The whole thing. So each factor is going to be divided by volume. And let's see what happens. Mass per volume here, that's going to go to density. Mass per volume here to density. That's to density. That's to density. But we still do have this force times distance. So we're going to hold off a second on that. And we can pull up part of the equation. So it's not going to quite be finished just yet. And we're going to force times density, or force times distance, excuse me, divided by volume. And we're talking about a pipe here. So I'm going to strengthen this out a little bit. We're going to have, instead of volume, we might say cross-sectional area times the distance that at which it moves from. So area times distance. And you might now see what we're going to do. Plus 1/2, instead of density, or instead of mass, we're going to use density times velocity squared, plus not mgh, but density times gravity times height, 1 equals, and your formula sheet's just going to say is constant, is the same, right? I'll write the whole thing out in a second here, but let's look back at this force times distance portion, right? We notice if our volume is area times distance, we have a distance over distance, that's going to cancel out. And the force over area, that is a formula we've already looked at, right? Our formula there is pressure. So really pressure. And this is a pressure differential. So what we're really going to rewrite this as pressure at maybe the beginning, pressure at an initial location. Let's move this over a little bit. Nope. Is equal to what? Pressure at our new location plus 1/2 density times velocity squared plus density times gravity times height 2. And so this is Bernoulli's law. It's really just a conservation of energy equation, and it looks like a lot, but here's what we'll say. A lot of times, some of these values are going to be 0. Typically, maybe this first height might be 0 if we get to a new height, or maybe both heights are 0 if there's no change in height. Density is going to be a constant, so we'll plug that in pretty easily. And maybe we'll have to use continuity equation to find both of the velocities. And typically in these problems, a lot of times we're asked to find maybe what's the pressure, right? Or something along the lines of this. So it might look a lot, but you're going to be given a lot in these problems. And it's mostly going to be just a matter of plugging in all our values and setting up our equation correctly. So that is the idea for fluids, right? We have two concepts. We have our continuity equation. The idea is as our pipe restricts down to a smaller diameter, the speed of that fluid is going to increase. It's going to go faster, right? Imagine putting your thumb over the end of a hose. The second piece, the link here, is that as our speed goes up, the speed of a fluid goes up, our pressure goes down. We have less pressure. So imagine either squeezing a toothpaste tube on the thick end so that it goes faster out the smaller, or imagine a tornado, right? The wind goes fast over the top, so a lower pressure causes lift to pull your roof off. And then finally, we have Bernoulli's law, which is just a derived conservation of energy equation. And all of those formulas you don't need to memorize. They're in the formula sheet. So you should now have a packet of practice problems that you can work on. So make sure you work your way through those. There should be a key with your sub, hopefully. This is 2025. If you're watching this a future year, maybe not, but go ahead and work your way through the continuity equation practice as well as the Bernoulli's law practice. And as you work together and check your work against the key. Hopefully you found this helpful and have a great day, and I'll see you all next time.